Okay guys, we're almost done looking at all these darn shapes. That doesn't mean that this will get any better or easier, but we're almost done learning about new shapes. So now we're going to start on our octahedral shapes. Okay. And our first example is going to be sulfur hexafluoride, my favorite gas. Okay, sulfur hexafluoride, 6 plus 6 times 7 is going to give us 48 electrons. And that is going to be, I'll cut to the chase, this guy right here. Can't forget these guys. Okay, so that is our sulfur hexafluoride. We have 6 electron domains, 0 non-bonding pairs. So that's 0 non-bonding pairs. So our molecular geometry equals our electron domain geometry equals octahedral. 2 square pyramids, butt to butt. All of our internal angles there are 90 degrees. Okay, so that does it for 6 and 0. And next up we have 6 and 1. And we're looking at, that should be phosphorus pentachloride, not boron pentachloride. I'm so sorry. I've probably caught that typo like half a dozen times by now. So phosphorus pentachloride, this is 5 plus 5 times 7 is going to be 40 electrons. It is not boron. Not boron, not phosphorus, but bromine. 7 plus 5 times 7 gives us 42 electrons. Yes, I am doing this more or less in my head. Okay, so bromine, 5 fluorines, is 10 electrons for 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Yep, I did my math correctly this time. Okay, so that leaves us with 2 electrons for a non-bonding pair on bromine. So we have 6 electron domains, 1 non-bonding pair. So our electron domain geometry is still octahedral. There's bromine in the middle. And it doesn't really matter where you put the non-bonding pair, because these 6 positions are all exactly the same on an octahedron. Okay? But I'm going to put it on the bottom because it'll make it easier to visualize the resulting shape. So there's bromine, here are our 5 fluorines, and there's our non-bonding pair. Okay, so when you connect these 5 fluorines together, there's the square on the bottom, then this one up top connects, you're left with a square pyramid. Okay, we finally have our classical Egyptian pyramid for the molecular geometry. Square pyramidal. So when you draw it out, just a nice square pyramid with the bromine, or the central atom is at the middle of the base. Then we have our fluorines at the 5 corners. Okay. So that is 6 and 1. And for our next trick, we're going to have 6 and 2, and that is xenon tetrafluoride. Yep, xenon can do multiple molecules with fluorine. So 36 electrons to play with. Xenon bonds to 4 fluorines. using up 8 electrons and leaving us with 28. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Leaving us 4 electrons that go on xenon as non-bonding pairs. So we have 6 electron domains and 2 non-bonding pairs. Our electron domain geometry is, of course, octahedral. So here is bromine in the middle. And now we have a choice for where to put our non-bonding pairs. Here's this non-bonding pair. The non-bonding pairs are super duper huge. They're going to get as far away from one another as possible. So boom. Goes on the opposite side, leaving us with fluorines at the 4 equatorial corners and making just a nice flat square or square planar molecular geometry. Okay. And here the geometry is nice and simple. All of the angles are 90 degrees because the squeezingness of the non-bonding pairs sort of cancels out. The fluorines are still nice and square. But over here, for this one, these 4 fluorines are squished up a bit, but there's so many fluorines pushing back against the non-bonding pair that it's kind of hard to see. So it's very, very close to a still ideal 90 degrees. It's very difficult to see. But we can see it because we have very powerful machines that cost lots and lots of money. All right. And that does it for the molecular geometries. Okay. So, is there an easy way to remember this? Not so much. I've never really come up with an easy sort of mnemonic or anything like that. I think just memorizing the 12 different shapes might be the way to go. Or maybe you can just, remember, the 5 electron domain geometries and then be clever enough to figure it out every single time. After all, for the most part, it doesn't matter where you put the non-bonding pair. The only time it matters is for our trig BP here, and then it's always equatorial. And down here for our octahedral, when we have 2 non-bonding pairs, they go on opposite sides of the pyramid. So if you can remember that, then maybe you can fill out this chart every time rather than memorizing the chart every time. So I already covered our bond angles. So now let's talk about extended geometries. Okay. We have only talked about binary binary covalent molecules because they're simple, they're easy to figure out. But the interesting molecules have extended geometries. They're much bigger. They do have very complex and difficult geometries when you have to work out very advanced stuff, grad school level stuff. But for intro chem, you can just treat different atoms in the extended geometry as being the center of one of the simpler geometries. Okay. So, for example, let's go ahead and look at these 3 organic molecules. Okay. Ethane, ethanol, and ethanoic acid. So, I'll go ahead and squeeze ethane in here. Ethane is C, because it's an organic molecule. Eth means that there are 2 carbons. And ane means all it has is hydrogen, so C2H6. So when you do this, you have carbon bound to carbon, then each carbon is bound to hydrogens. Okay. And this is what ethane looks like. Okay. I drew it this way because I sort of wanted to emphasize the fact that you do have this extended, expanded, three-dimensional geometry going off in all directions. Okay. For larger molecules, it can get very difficult to try and draw that sort of thing. So we don't. But you can do it with something small and simple like ethane. You can also look at each carbon atom independently. So here's a carbon all by itself. And here's a hydrogen. Here's hydrogen. And here is hydrogen. Then down here, CH3. So carbon and 3 hydrogens makes CH3. So you can just look at each carbon atom as the center of a simpler geometry. That's what I was saying there. So you can see it's just a tetrahedral center. And if you look over here at this other carbon, it's exactly the same. Okay, there's nothing to differentiate the two carbons. So each one of these carbons looks around itself and sees 1, 2, 3, 4 electron domains. Each one of these carbons has a tetrahedral geometry. And then I've run out of room even in my expanded workspace. So I'll just go ahead and fudge it. Okay, so ethanol is C2H5OH. All we've done is replace one of the hydrogens with a hydroxyl. You remember that from your polyatomic ions. It's a sort of a hydroxide, only it's bound very firmly to the ethanol. It doesn't pop off. And what you see is carbon bound to hydrogen. Let's see. Okay, so carbon, carbon, hydrogen, 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 hydroxide. So we'll focus on this carbon. We have CH3, OH, H, H. So even though that carbon on the right is bound to lots of different things, it still only has 4 electron domains. It still has a tetrahedral geometry. It's going to be slightly distorted from a perfect tetrahedral geometry just because you have a hydroxide and a methyl, or sorry, a CH3. Those are, different atoms, different elements. They have different shapes because, this CH3, it's a whole other tetrahedron over here, right? So it's going to take up more space than just the hydrogen, which is just, a proton, right? And it's also going to take up different space than oxygen bound to a hydrogen. The oxygen bound to hydrogen, there are 2 non-bonding pairs that I didn't show, so it has its own bent geometry. So you can look at the different places, the different elements, the different atoms involved, and look at their individual geometries. Now we scoot over just a little bit, and we have ethanoic acid, aka vinegar. Okay. That's just C2, let's see, I can go ahead and draw it. CH3COOH. Okay, that's one way to put it. Okay, so ethanoic acid, you have carbon double bonded to oxygen, bound to oxygen, bound to a hydrogen. Okay, so that's where the COOH comes from. Then that's bound to carbon with 3 hydrogens on it. Okay, so that's ethanoic acid or acetic acid or just plain old vinegar. Okay, and so now we see we have different geometries. Okay, this carbon here only has 3 electron domains. Okay, it has a bond to the oxygen, it has a double bond with this other oxygen, and then a regular single bond to the carbon. 3 electron domains means this carbon is trigonal planar. But this carbon over here has 4 electron domains, so it's still tetrahedral. This guy over here is bent. Okay. So extended geometries means you get multiple smaller geometries, one at each center along the chain, as it were. So even though the whole molecule has a very complicated geometry, you can look at the individual centers, the individual atoms within the chain or along the molecule to analyze, local geometries. And you can still understand the molecule as a whole in that way. And that does it for talking about geometry qua geometry. When we come back in the next lecture, we will be talking about one of the applications for geometry, to wit, polarity.